This video is a walk through the Kepler Exoplanet Transit Hunt. It's about the science of planet discovery, and it's got some math, but we'll help you through it. The basic idea of the lab is to discover a planet by staring at a star and looking for a tiny drop in brightness when a planet passes in front of it. When a planet goes in front of a star, that's called a transit, and this planet finding method is called the transit method. We can't even see the exoplanet, but we can find out information from the star the exoplanet is orbiting. To start things, drag the telescope view circle over to the blinking star. You see an animation of the planet orbiting the star. Notice the planet is orbiting horizontally. That's one of the orientations where we can observe a transit. If the planet orbit's plane does not line up with us edgewise, the planet will be out of our line of sight with the star. Pick a star to investigate. Notice all the spectral types. Spectral type is a handy way to sort stars according to properties connected with the star spectrum. Properties such as size, temperature, and mass. We're not interested in very large stars. We're interested in stars similar to our sun. For example, our sun is a G-type 2 star. Now let's get started with G3 here on the left-hand side of the screen. The chart on the third screen shows mass, size, and temperature of various star types. At the bottom of the screen, there's a note bar to keep a record of our findings. There's no export function for these notes, so it's a good idea to keep a permanent record on a piece of scratch paper in front of your computer. Mass and radius are both compared to our sun. So a star with the mass of 1 has the same mass as the sun. Likewise, a star with the radius of 1 has the same radius as the sun. Temperature is measured in Kelvin, where 0 is absolute zero, or no molecular motion. To use the note bar, type in the number or click and drag the matching box color in the data table to the matching color space in the note bar. Do that for all 3 star properties, mass, size, and temperature. Then click Next. Now collect some data. Keep your eye on the star that is in the blue circle. The Kepler Space Telescope had done this for over 150,000 stars simultaneously. After you click the Start button, every time you see the star blink, click the button that says Record Blink. By the time you're done, the graph you've created will be for star brightness versus time, and it's called a light curve. Now we're going to make measurements. First, the planet's orbital period, the time it takes for it to go around the star once. Measuring the space of the brightness drops along the x-axis. You can drag the x-axis up to a line up with the particular brightness drops. That's a really easy way to help measure the orbital period in days. Type the number in the note bar in the blue space that says exoplanet orbital period. Then measure how deep the drop in brightnesses are. Drag the y-axis to line with one of the drops in brightness to measure its depth. Type that number in the note bar in the yellow space that says % brightness drop. What would a 100% drop in brightness mean? The star's light must have been completely blocked. In reality, a planet blocks less than 1% or 2% of its star. For really small planets, it can be 0.01%. Be careful in reading the brightness drop scale to make sure your decimal point is in the right place and you've counted the scale of divisions correctly. Now click Next. Over 400 years ago, Johannes Kepler figured out 3 laws governing the motion of planets in our solar system. One was that the planets have orbits shaped like ellipses, not perfect circles. Another described how a planet moves faster in the parts of the orbit where it's closer to the sun. His third law says the longer a planet takes to orbit the sun, the further the planet is from the sun. The NASA Kepler team used that law, Kepler's third law, to find out how a planet orbits from its host star by measuring its period. Even if you don't know algebra, you can see that the greater the period, the further the planet is from the host star. The formula is pretty straightforward. For a star's mass, m equals to 1, a star with the same mass as the sun. The formula is pretty much how Kepler originally wrote it. The formula has a built-in calculator button. Just drag the right color-coded planet and star properties from the note bar up into the equation. But wait, the formula expects the period in years. Oh no, we made our period measurement in days. We need to convert that to years. There's a convenient convert button that automatically divides by 365. Now press calculate to crank out the planet's distance from its host star. Its astronomical units, or AU, 1 AU is the average distance from the Earth to the sun. That's about 150 kilometers or 93 million miles. Before you click the next button, drag the purple box in the formula to the purple space in the note bar so your answer gets recorded there. So far, we have found the planet's orbital period and average orbital radius, or the distance from its star. Every star has a zone around it where there could be planets able to sustain life. Such a zone is called the star's habitable zone, or Goldilocks zone. Such a zone must allow for liquid water. All life forms we know of require liquid water. For a planet too far from its star, if there is water, there's only solid water, ice. For a planet too close to its star, if there is water, there's only water vapor. What other factor besides distance from the star affects a star's habitable zone? The star's temperature. The hotter the star is, the further away it is from its habitable zone it'll be. On screen 6, you adjust two things: the star temperature using the white up and down arrows, and the planet distance using the white sideways triangle arrows. And those sets of arrows to match the star temperature and planet distance with the values you have in the note bar. You can then write yes or no, or Y or N in the bright blue space labeled habitable zone in the note bar, then click next. Now we can add to our list of planets' properties whether or not the planet is in the star's habitable zone. Can we figure out what the planet's temperature is? This depends on some of the factors: star temperature and planet distance. This formula is also known in physics as the black body radiation formula. There's one factor that matters: the star radius. You can learn about this in a physics course. Also, this formula ignores any greenhouse effect. Greenhouse gases in the planet's atmosphere might raise the temperature, so the temperature we calculate here will be a low-end estimate. The planet's actual temperature may be higher. To use our black body radiation formula, just drag the star's radius, star temperature, and planet distance from the note bar into the formula and click calculate. Then drag the calculated planet temperature into the note bar. Chalk up another item to our growing list of planet properties we just got straight from Starlight. Can we figure out the size of our planet? Well, bigger planets create bigger dips in brightness, so we can figure out how big the planet is. The percent drop in brightness depends on the area of the star that is blocked by the planet. If you have learned that the area of the circle is pi times the radius squared, then the equation on the planet screen will make sense. The brightness drop is simply the area of the disk of the planet divided by the area of the disk of the star. With some general algebra and a square root, you can get this formula. Even without algebra, you can see the planet's size is related to the drop in brightness and star size. Just drag the star radius and brightness drop from the note bar into the equation, then calculate and drag the resulting exoplanet radius into the note bar, then click next. Yet another planetary property added to our list: planet size. That's a lot about the planet we learned from just Starlight: the planet's orbital period, orbital radius, whether or not it's in the habitable zone, planet temperature, and planet size. Amazing. The ninth screen shows a summary of your investigation with an artist's conception of the planet. The size shown is compared with Earth. A printout or screenshot of this page can be your permanent record for this assignment. The final window shows an artist's conception of what the surface of your planet might look like. You can pick another star to investigate too. Good hunting!